Okay.
Hello everyone, today we'll be presenting on a cutting-edge approach to enhancing our electrical power grids through the use of minimum spanning tree algorithms. Our presentation is structured into 5 key sections: introduction, context, well-defined questions, and analysis, conclusion, each providing insights into different facets of MST application. Let's consider our current electrical power grids. These are vast and complex networks comprising power stations connected to substations through a web of transmission lines. The efficiency of these networks is heavily dependent on the optimal arrangement of these connections, an aspect that is central to our research and application of MST algorithms. MST algorithms offer a fresh perspective by identifying the most effective connections within a network, thereby forming a tree with the shortest total length. This is more than a theoretical exercise. When applied, MST-based designs can significantly reduce energy losses in power transmission, leading to a marked increase in the overall distribution efficiency of our power grids. Going further, we explore how these algorithmic solutions can determine cost-effective connections between substations. By minimizing transmission line lengths, we not only save on infrastructure costs, but also enhance resource utilization, resulting in a more streamlined and reliable electricity distribution. Graph algorithms are incredibly versatile. They are used in various fields from social networks to logistics. In our case, they provide a powerful framework for modeling and improving the electrical grid, showcasing their wide-ranging applicability.
Thank you, Neeraj. Moving forward, what are the advantages of MST when we apply for power grids? For example, we can increase the we have optimized power grid. We increase the efficiency. We have less failures when compared to without implementing MST. If we don't have other alternative solutions, the failure rate will be high. But if, for say example, if one set of power grids fail, we have other lines from which we get the power supply. So there's a continuous flow of power supply. So the impact of failures is lessened. Since we are using MST, we always try to have the optimal path, the shortest distance for the the power to flow through, the electricity to flow through the lines. So in that way, we'll be reducing the wastage of current. So which at the end of the day enhances our reduces our carbon footprint. So so how are we applying MST to this? So what are the questions we're gonna answer by while applying MST? So at the first, what are some of the graphs algorithm that we can apply to the electric power grids? Next question happens to be, what are the MST algorithms we're gonna apply for the electric grids? Then the next question is, how are we gonna build a fail and safe secure electric power grid so that we still have power if some set of power grids fail?
Thank you, Anika. As my teammates mentioned earlier, we gave a lot of context about how MST algorithms could be applied to, solving electrical power grid problems. We also spoke about the questions that we're trying to answer using these algorithms. So some of the graph algorithms that can actually be used to solve this problem are the two famous ones. One is Kruskal's algorithm and one more is Prim's algorithm. Both of them have the same end goal where the algorithm tries to generate a minimum spanning tree from a given tree structure or a given graph. So I'll explain individually each algorithm, how they work and how we're applying them to our problem. So first start with Kruskal's algorithm. So the algorithm first sorts the edges from low weight to high weight. Next, it takes the edge with the lowest weight and adds it to the spanning tree. If the edge that was added to the spanning tree, if it creates a cycle, then it rejects the edge. If it does not, it continues to add the edges until we reach all vertices and minimum spanning tree is created from the initial graph that was provided. That is the high-level summary of Kruskal's algorithm. Next, if we see Prim's algorithm, the algorithm first initializes a minimum spanning tree with randomly chosen vertices, which you can see in the for loop in the first 3 lines of the code. Then next, the algorithm finds all edges that connect the tree from the first step with the new vertices. From the edges found, it selects the minimum edge and adds it to the tree. And the second step is again a loop iterative process where it is repeated until the minimum spanning tree is found. So both Kruskal's and Prim's algorithm are greedy algorithms. So you can also see how they differ from each other. So some of the differences that that you can draw from Kruskal's and Prim's algorithm is first, the Kruskal's algorithm generates the minimum spanning tree from the least weighted edge. Meanwhile, Prim's algorithm generates the minimum spanning tree from the root vertex, starting from the root vertex. And Kruskal's algorithm runs faster for sparse graphs, and Prim's algorithm runs faster for dense graphs. If we talk about the time complexity of each of them, Kruskal's algorithm time complexity is O of E log V, where V being the number of vertices and E being the number of edges. So this is a logarithmic time complexity. Whereas when you see Prim's algorithm, it is so the time complexity of Prim's algorithm is O of V square, and V being the number of edges. Here it is polynomial time complexity. So next, so that was about the first question in our questions that we had defined earlier, where we answered what algorithms can be applied to our problem. So next question is how we are applying those MST algorithms to solving the power grid problem. So we can imagine the electric power grid as a graph, which can be represented as a graph or a tree, and various nodes within the tree are the various nodes within the power grids, such as generators, substations, and transformers. And the transmission lines that connect each of these components could be represented as edges. So our goal is to find a subset of edges that connects all the nodes while minimizing the sum of weights of these edges, which is nothing but a minimum spanning tree. So to find, so this is our proposed solution to apply MST to electrical power grids. So in the first step, we collect data regarding the power grid's current state, where we collect data from the locations of the substation, the cost that is required to transmit power from one station to the other station or from one node to the other. Similarly, we collect all the data points and create a graph out of it. So once the graph is constructed, it can be converted to a computer science algorithmic problem where an MST algorithm can be applied to determine the optimized network structure. And then once the optimized network structure is obtained to us, since the minimum spanning tree gives the least weighted edges by connecting all the nodes within the graph, so this is a cost-effective way to transmit power from any node in the graph. So yeah, so as I mentioned, the result of the spanning tree is a least cumulative weighted graph, which gives the shortest path to transmit power between any two nodes in the graph. And also Vinayaka mentioned on the topic that the MST algorithms can also contribute in designing to fail-safe networks. So this can also be seen in the last point where if one set of nodes fails, the MST algorithms can be applied to find alternate minimum spanning trees that can be used to transmit electricity without any failures.
Thanks, Rakshak. So, moving on to the implementation, the dataset for the study is sourced from Texas A&M University's Energy and Power Group researchers. It has a large-scale synthetic model representing the combined electric grid and the natural gas pipeline system geolocated in Texas. And the dataset features electric buses, which are around 7,000 nodes, and the natural gas nodes. A sample from the dataset includes node information such as location coordinates, power, and the flow rates. So if we could go to the code, Raksha, can you open the code? Yeah. Thank you. So here we are constructing our minimum spanning tree. We've implemented Kruskal's algorithm. So we utilize the Harvesting formula to calculate the geographical distance between the nodes on the Earth's surface. This is important for accurately reflecting the real world distances in our electrical grid network. Our approach started by loading a comprehensive data set of the GRIDS node, which includes information like location coordinates and the power flow, allowing us to build a realistic model of the GRIDS infrastructure. By iterating over each pair of nodes, we assign weights to the edges, connecting them based on the calculated Harvesting distances. This weights represents the potential cost and energy loss associated with the each connection in the grid. Kruskal's algorithm was applied to this weighted graph to find the minimum spanning tree. The algorithm selects edges in the ascending order of weights, ensuring no cycles are formed to connect all the nodes in the most efficient way possible. And the final output from this process is a list of edges that make up the optimized grid. This optimized set of connection minimizes the overall grid length, reducing construction cost and the energy transmission losses. So as we see in the output, the weights of an edge in this MST represents the calculated geographical distance between nodes, which corresponds to the potential transmission line lengths. Edges with very small weights demonstrate the algorithm's precision in choosing connections that are close together, thereby reducing the amount of wiring needed. And the edges with the larger weights, as seen below, are the longer connections within our MST. They are crucial because they represent the longest stretch of power lines that would be necessary to connect all substations in an effective manner. And the next one is to construct the minimum spanning tree. Here we have implemented the Prim's algorithm. We calculate the distance between nodes using the Harvesting formula, again same like Kruskal. Uh, Prim's algorithm begins with an arbitrary start node, progressively building the spanning tree by adding the nearest unconnected node to the tree at each step. So at every iteration, the algorithm updates the minimum distance to connect each node outside the tree and selects the edge with the smallest weight to add it to the MST. And the output of the algorithm provides us with a set of connection, each represented as an edge between two nodes, along with the calculated weight, which corresponds to the distance. If we could go back to the slide. Um, yeah, and the next slide, we have the figure. Yeah, this figure illustrates the minimum spanning tree of an electrical grid network. So each blue circle there represents a node. The number displayed above each node denotes the unique identifier for that particular node. Edges which are represented by lines connects the node, and these connections are chosen to ensure the overall length of the distribution path is minimized, which is the fundamental aspect of reducing transmission loss and costs within the grid. So the absence of any intersecting lines suggests that the MST successfully avoids unnecessary redundancy. Moving on to the summary, which will be explained by Vinayaka.
Thanks, Deepak. So in conclusion, we can see that the application of the graph algorithms on electric grid offers a promising avenue for optimizing their layout and improving their usual resilience. And MST approach contributes to determining the shortest weight for the distribution, as we explained. So, so in summary, we can say that we have an application for computer science algorithms like PRIMS and Kruskal in real world problems. For example, this power grid, applying power grid, applying MST to the power grids, as we told the advantages, it's gonna in long term it is gonna save our planet. It's gonna reduce our carbon footprint. That's it. Thank you.